So this event is can you all hear me? By the way, okay. Yeah. So yeah, we'd like to start our session, and so today is our week 9 session. So before starting our session, let me introduce you a little bit about our Women in AI. So this event is hosted by Women in AI across the different ABRED chapter. And my name is Kaiser from the Women in AI ABRED chapter, and I will be your host for the today's session. So Women in AI is a non-profit organization working to make AI more inclusive globally. And we are founded in 2016 and over 18 members and across the 140. So for the APAC region, we have Australia, Taiwan, Myanmar, Singapore, Japan, India, and much more. So this community is really about the women supporting other women to create an empowering, inclusive, and diverse network through hosting various type of event like this one. So of course we have each chapter run their own types of event in their local country throughout the year as well. So the next big event coming out in Women in AI Award will take place in next year in June to celebrate an amazing achievement of women in the STM. So we hope to you all see in there. So Feel free begin to be part of this amazing community by scanning this QR code in the left corner, and please do not hesitate to reach out to us if there are any additional questions. Okay. So we are hosted the Women in AI MN Paper clubs since October, and now currently we are in the week 9. And so let me little bit recap our session. And in our week 1, we did the keynote session of the MM paper reading class, and then week 2, this event is hosted by the Women in AI Philippines chapter, and they share about zero-shot learning throughout cross-border transfer topic. And in the week 3, is hosted by the Women in AI EU chapter, Australia chapter, and Angela came from the Women in AI EU chapter explain about the introduction to the ROC analysis, and then followed by the Women in AI Singapore chapter, and they bring out the adversarial AI class distance hardening paper, and then followed by the Women in AI Myanmar chapter, they share about the learning from the imbalanced data. And then week 6, we use the same topic again with another volunteer, with the help of other volunteer, and explain about the different perspective of the same topic. And in the week 7 session, it hosted by the Women in AI Malaysia chapter, and so they introduce about the abuses comment identification on the Indonesian social media data using hybrid deep learning paper. And last week we have the session with the Malaysia chapter 2. They also bring up the topic of surveys or clustering algorithm. So for this week, we bring up the topic of machine learning, trans, perspective, and prospect. So we were in this for this week session, we invited the speaker from the Australia. So he is his name is Hosein, and he is the senior machine learning engineer at Siemens. So he will be here with us to host our session. So hi, Hosein.
Hello.
Yeah. Okay, we can hear you.
Yeah, great.
Yeah.
Okay.
Yeah.
Okay.
I will start my screen share, and you can start it. Yeah. Okay. Where is this? Got it.
Okay. Can you see my screen okay?
Yes, I can see the screen.
Great. Okay. So thank you, everybody. Thanks for giving me this opportunity. I'm really happy to be here. Like she said, my name is Hosein. I'm a machine learning engineer at Siemens. I come from a background in astronomy, really. So I'm an astronomer. I'm pretty sure none of you know what an astronomer is, so I'd like to explain it. Astronomer is an ex-astronomer. So I used to do astronomy, where I use artificial intelligence and different machine learning techniques to understand how the universe works. At that time, my job was to analyze the images that we take using Hubble Space Telescopes from images from deep in cosmos, from 8-9 billion years ago all the way to now. And I came up with a scenario for how galaxies work, how they change their shape, and all that. And all that scenario and all the papers that I published were based on machine learning techniques. And it was so powerful, it was great. It was some part of my life that I'm so proud of, because I was trying to answer a big question. And then I moved out of academia and I joined Siemens, where I use again machine learning techniques to now help trains all around the world to run safer and smoothly. Right. So it's great that we have such tool in hand, machine learning, I mean, that we can use it in many different directions. At least in my small bubble, I've used it in astronomy, and now I'm using it in industrial spaces where we monitor trains using it. And I'm pretty sure all of you are using ML techniques for any a different application, and that indicates how powerful it is. So with that in mind, let's dive into this paper published in Science: Machine Learning Trends, Perspectives and Prospects. So the paper is a kind of a review on where we are in machine learning. It explains a little bit about what is machine learning, how does it work, and gives an overview of what is this technology. It also explains the three main categories of machine learning algorithms, in particular supervised learning, unsupervised learning, and reinforcement learning. We'll talk about them a little bit, and then it also talks a little bit about the different applications of machine learning and some challenges that we have when we use data. For example, the amount of data that we have, the exploding amount of data that we have, what should we do with them, and how should we take care of privacy and all that. So it starts with what is machine learning, and machine learning is our effort to build another brain, a brain that can somehow learn the tasks that we teach it, right? And then gives us our desired output, right? And in many cases, it happened that our machine learning algorithms are better than us as human beings, right? And we have seen this many times. When computer could beat Garry Kasparov in chess, when AlphaGo could beat the Go champion, Lee Sedol, when we could solve a protein folding problem with AlphaFold, and many other samples that we have seen, we have seen that machine learning algorithms can work better than us, right? In another example that I'm pretty sure that all of you know is the ImageNet contest that I think it was started 2007-8 or something like that. And then before the emergence of convolutional neural networks, all the machine learning algorithms were not as good as human performance. But after the introduction of convolutional neural networks around 2011, 12, or something like that, we saw that how powerful this technology is, and it is already doing a better job than human being. So it's amazing. So yes, this technology is both smart and stupid, is both promising and scary, depending on how we use it, how we train it, and in what application we're using it. So we should be worried, and we should be simultaneously proud of ourselves that as a human being, we came up with such technology. So it goes on and talks about, in the introduction, it comes and talks about different applications, like I briefly told you. Talks a little bit about the applications of machine learning techniques, and it also introduced machine learning as a system that, like I told you, it's like a kind of black box. If you want to think about it like that, you give it an input, does some processing, and gives you the output. Right? We already had this black box system, but this one is now very, very powerful. So, all right. So I'm reading over this. Many developers of AI systems now recognize that for many applications, it can be far easier to train a system by showing it examples of desired input-output behavior than to program it manually by anticipating the desired response for all possible inputs. So it used to be the machine learning that we used to have, like late 90s or early 2000, was that we would write a huge lookup table, a huge dictionary to describe, like, say, a cat, right? A cat has this kind of, say, eye, this kind of ear, this kind of tails, and all that, right? And then when you give the system the image of a cat, it would go and look up between these lookup tables and see if it matches those parameters. If it does, then that's a cat. Otherwise, say this is a duck. This is a stupid example that just came to my mind, but it was like that. That was how we knew the machine learning techniques. But then we figured out that this is not the way to approach this problem. We should come up with a solution that we just show how our data looks like, and it gives us the output. Right? Then we came up with this kind of solutions, in particular with convolutional neural networks. We came up with this solution that you don't need to describe what is a cat. You don't need to describe the properties, characters, nothing. It understands by itself, right? It takes the features out by itself, and then it understands what a cat is. So all we need to do is to give it enough pictures of a cat so that then the algorithm understands what a cat is, what a dog is, right? So another example that here the paper is talking about, what is a machine learning algorithm, and it comes to the point of input-output pair, right? So for example, in learning to detect credit card fraud, the task is to assign a label of fraud or not fraud to any given credit card transaction. The performance metric to be improved might be the accuracy of this fraud classifier, and the training experience might consist of a collection of historical credit card transactions. So, as it's an introduction, the paper is introducing what is the problem, what is the data, and what is the desired output. right? Which is three main components of a machine learning system, right? So first of all, we need to understand what is the problem, which is to distinguish between fraud and non-fraud, not fraud transaction. What is your data, which is historical credit card transactions, and the output. Like I said, the output will be fraud or not fraud, right? With the data being historical transactions. Now, for optimizing such model, we need a metric. We always need a metric, and most of the time, this metric it's the accuracy of as a performance metric. The accuracy is most of the times the best one. So so yeah, that's the performance metric that's the paper is talking about. All right. Okay. I think I would like to wrap up the introduction, but before that, in a nutshell, the what is this about is that we need to embed the problem into a function, right? A function that you give it an input and it gives you an output. So in the fraud not fraud problem, right? We embed the problem into a function, and then when we optimize this function with it, and you provide an input like being like a new credit card transaction, right? It processes the problem, and the output will be those two outputs that I just said, fraud and not fraud. So I'm pretty sure all of you are familiar with these kind of introductions, but because the paper is kind of really an overview, it doesn't go into too details of any of these things. So it's just an overview. That's why it might be boring for a lot of you guys, but that's we're here to talk about this paper, so we have to stick to this. Okay, so before we wrap up the paper, the introduction, I would like to also read a part of this paragraph, where it says that when you're dealing with a machine learning problem, you need to optimize three main properties, right? The first one is the sample complexity. Obviously, you need, like I said, you need the sample data to train your model, right? So you need to come up with a trade-off between these three parameters. The first one is sample complexity. The second was computational complexity, and the third one is your feature complexity, right? So, for example, you may have a very nice algorithm, but it requires like trillions of data to train, to learn what is a cat, say, right? So you need trillions of images of cat, which doesn't exist. So your algorithm is useless. Or you may have a good algorithm, right? A good network that requires a fair amount of data. So the data is not complex. So the first one is fine, but you need a lot of computation power. So you need the whole, like 10 times all the supercomputers on the earth to train the model. This is not how to do it, right? So you need to optimize the computation process as well. The third one, which is very important, is where you put together your features. When you engineer your features, like for example, in tabular data, it's not the case for convolutional neural networks, because then there we find our features, and the network finds our feature using the convolutional layers and all that. But for, like, say, a tabular data, a lot of times we need to come up with the best feature properties, right? That we call them feature engineering. So you cannot come up with you cannot give a model like 1 million features, right? That's not how it works. It's very likely that most of those features are useless. So they play, they have zero effect on the decision making of the process of the network. So your network doesn't need all those features. You need to come up with a fair amount of features, not 1, 2, not millions of features, right? A lot of time with tens of features, 5, 10, 20, 30, 100, something like that, depending on the problem, you can solve the problem. So finding the optimized number of features and only coming up with the amount of features that you need is a very, very key point. So again, this is so important. So I would like to repeat it. You need to optimize 3 main components: sample complexity or data complexity, computational complexity, and feature complexity. 3 main components. All right, let's move on. And then the paper right after this, the paper talks about the drivers of machine learning progress. What was the main reason that machine learning algorithms could make such a difference in the world? And all of us know that big data was from the early years of this century, we started to find a lot of data. In science, we used to have a lot of data, like, for example, astronomy, biology, and all that. We used to have a lot of data, but it wasn't as much as it is. But then on top of this, we started to have Facebook. We started to have Google. So all these great platforms, large platforms, started to produce a lot of data. Now, people were, banging their head against the wall to understand, to see, okay, what should we do with this data? Right? There are a lot of data that you can use, you extract information, but we didn't have enough powerful enough algorithms to use when we wanted to extract this information. Right? So that was the golden point, the golden time that machine learning came into play. So big data. I just highlighted astronomy there, just because I come from astronomy background. So when the paper was talking about some the explosion of data in different fields of science and technology, in between them there was astronomy, where we know that these days we have huge amount of data from all telescopes all around the world, and it's really impossible for people like old days to go in person and look at images of galaxies one by one. That's not the case anymore. So we need really, really powerful algorithms to deal with this kind of data. And the same for neuroscience, the same for genetics, and all these fields. Most of fields are becoming data intensive fields. So data, that we have the explosion of data in all these fields, and we need to come up with the best solutions, which has happened to be machine learning algorithms for finding information. All right, so the paper now goes and talks about the main methods in machine learning, starting with supervised learning, and then it goes and talks a little bit about the unsupervised learning. I think it touches semi-supervised as well, but doesn't go into details really that much. And also talks a little bit about the reinforcement learning as well. But supervised learning is the main part that the paper is donating a lot of its space for explaining supervised learning, and that's fair enough, because it's been the first the field of machine learning that's been developed, kind of, and it's been used widely in industrial applications. and it's very mature, and so that's fair enough. So in supervised learning, as most of you know, we have pairs of say pairs of X and Y, right? So you have two say so as paper says, collection of X and Y pairs, right? And the idea is to come up with a system that when it sees a new X, let's call it X star, it can give us the pair, the new pair, it can predict the pair, which is Y star in this case, right? Say, for example, in spam classifier of emails, we have spam, non-spam, right? Two classes. So it's a binary classification, really. If we didn't have this system, we should really, kind of close our laptop and go crazy, because our mailboxes will be flooded with too many of spam emails. So thanks to machine learning algorithms, we have this kind of algorithm that does most of the job for us, makes our mailboxes very, very clean. So okay, so like I said, supervised learning is when we have labeled data. So we showed the network what are the data look like, and so which are X's, and what are the output look like, what are the desired output. Say, for example, I show the model, this is the email, and I know that this email is labeled as spam. So X is this email, and Y is spam. And then when I show it another unknown, unlabeled data as X star, I expect the model to predict the Y star for me, which is either spam or non-spam. So that's a binary classification. But we also had have multi-class classification, or that instead of only two classes, you have multiple classes. So in summary, I also have to be all right. Now I have some time. So in a nutshell, you kind of translate your system into a mapping function. Say, let's call it fx, right? So you come up with a function, and the idea is to optimize this function for that can give us a y value, an output, with any given x, right? And when you already have x, have shown your model some labeled x, then that is called supervised learning. Some just okay. Some here the paper just shows some some examples of supervised learning, or sorry, some of the mapping functions, the fx that I just told you. We have like decision trees, random forest. Random forests are just a combination of some multiple decision trees. We have logistic regressions, which is nothing but classification. Just historically, it's been called logistic regression. Regression themselves, SVMs or support vector machines, and neural network kernel machines, as well as Bayesian classifiers. So these are the functions that we optimize. So, like for example, in case of decision trees, it processes your input, walks it through some branches, and come up with the best decision, which is our Y. Okay, it also touches the deep neural networks. as a very important supervised learning method. Well, these days, deep neural networks are also used for unsupervised learning as well, but they've been mostly used in supervised learning, where you have and deep neural networks are nothing but sequence of multiple layers that each layer comes up with an abstract representation of your input. Say you show it the image of a cat, and then each layer comes up with different representation, right? With convolutional layer, pooling layers, and all that. Each layer. So, for example, say layer first comes up with some linear features. The other layer comes up with like round layers or eyes, for example. The other one finds the backgrounds, for example. The other one comes up with some representation of ears and all that. And the combination of all these will train the model to understand what a cat is. So that's deep neural networks. It touches a little bit on that, and it just the images that are shown in this paper are not really described in detail, but here it shows how we can use deep neural networks for image captioning. That say, for example, we have an input image. We run this input image into a CNN that gives us, feature maps. That, like I said, there are different representations of this input image being a bird. Then you parse this feature maps into a recurrent neural network and an LSTM, and based on the attention on different part of the image, it gives you the information represented as words. So, say for example, it looks at two wings and says, okay, only this. It looks at the center of the image. It figures out this is a bird. It looks at I see only two wings. Then so this is a bird, not multiple bird. The wings are they're not collapsed, so the bird is flying, and it then it sees water based on the attention that it gives around the bird and all that, right? You get the idea. So this is a kind of example that the paper almost talks, says nothing about that, with no details, which is surprising. Well, it's a science paper; it has to be short, but I would expect the paper to explain images a little bit. You either don't show any image or you explain them. That's the way to show images in a paper. And then the paper talks a little bit about unsupervised learning, which is extracting information without labeled data. So you have unlabeled data, and you try to understand what this data is telling us. Like, for example, K-mean clustering. It's a clustering algorithm that it works without labeled data. Right? So you don't need to spend time for labeling data. Comes with some limitations, but it's very promising. It's very promising because at some point we need to go towards this unsupervised learning algorithms, because we cannot keep labeling all the data in the world. Right? So we need to come up with solutions that work with no labeled data. It also talks a little bit about, I don't want to go through any details here, but it also talks about dimension reduction as an unsupervised method. Okay, here it also talks about the clustering algorithm, right? As in addition to dimensional reduction method, it also talks about clustering methods as another unsupervised method. Then later on it goes and talks about the reinforcement learning. Now, reinforcement learning has been a very RL has been a very promising field in machine learning because it gives you the chance to interact with the model, and that's amazing. And the most important things that we have seen was when DeepMind solved the problem of Atari, right, for playing Atari game. Then we had AlphaGo and all that. They're all based on reinforcement learning. And then in reinforcement learning, what you have really is you have an environment. I actually have a slide here. So okay, yeah, I hope you can see this. So you have an environment. Say, for example, your house is an environment and then you have a cat as the agent. So you have an environment, you have an agent that can do something in this environment, right? And then you have a state, which is the situation of your system. So like cat is sitting is a state, right? Now, you send some information to your cat, right, as action, right? Say you call your cat, come to me, that's an action, right? And then the state changes from sitting to walk. And then a very important part is the objective function, a reward, right? The cat has to receive to understand that this was the best action, which is the fish as the reward. A very important part of reinforcement learning is the reward function, is the objective function. That has to be defined very, very carefully. So if the action is along with your policy, we also have policy. We don't want to talk about that. But if it's along with the policy, then the agent gets rewarded, otherwise gets a penalty. Right? So you need to be very careful when you define this function. I think some of you have seen the monkey, and the paper also mentioned that. A notable example being the use of reinforcement learning algorithm to predict the response of dopaminergic neurons in monkeys learning to associate a stimulus light with subsequent sugar reward. Right? So you see the action, the light, and then reward, sugar rewards. I'm pretty sure most of you have seen the video of a monkey that does something and gets rewarded by some sugar syrup or something through its mouth. Okay, let's. All right, well, I'm getting towards the end of the paper. It then talks about the emerging trends. Gives us some examples of emerging trends that with the amount of data that we have these days, we can do a lot of stuff. For example, in recommendation systems, that we know that YouTube is working based on recommendation systems, Netflix based on recommendation systems. The next image that you see from one of your friends in Facebook or TikTok or whatever is based on recommendation system. So it's a kind of your interaction with the system. So recommendation systems are the system that machine learning system that has made most of money in between all other machine learning algorithms, right? if we didn't have recommendation systems, Facebook couldn't make all this money, Google couldn't make all this money, and you know, it's a very powerful tool. Anyways, so yeah, the system works in a way that it predicts what is the best for you to see based on your previous behaviors, historical behaviors, and the prediction is what is best for you to see. That's recommendation system. It also talks a little bit about you know, in terms of an ecosystem where a machine learning system works. It's getting more and more complicated because we need large-scale parallel and distributed computing platforms. And it also shows one of these platforms here, where you have, you know, say, streaming of data coming here, and some of us use Spark for, you know, for taking care of streaming data, and then you use different technologies like Spark SQL and all that. And then, you know, ML is really only this part. But to get the ML network to work these days is not like 10, 15 years ago or something like that. It's been really amazing. We've seen really amazing, you know, progress in the ecosystem that an ML model works in. So yeah, okay, we don't want to go into these details. These are mostly like ML ops and stuff like that. Another emerging thing is, with all this data comes the concern that we have for our privacy, really. So all this data are our data. We might not be happy for it to be used by large corporations to make money, right? This is a real concern that the paper nicely mentions. And also it also says that most of us might be happy for our data to be used for some, you know, society, for a good cause. Like, for example, I'm happy for my data to be used to control, you know, COVID-19 pandemic, right? If you use my geographical data, my location, to identify where are close contacts and all that, I'd be happy to provide that. But currently, there is no infrastructure for us as users, as the owners of data. I mean, it is our data, but we're not really owners of data, right? And that's because, again, we don't have that infrastructure. If we had that infrastructure, it would be great if we could, like, hey, Mr. Google, you have my consent to use my genomic information for tackling the pandemic problem. Or if you want to use my information to solve a disease problem in Kenya, okay, for free, you can use it, right? All right, there's something. Should I reconnect or something? Was that for me? Fine, or
yeah, me and my team can see your screen and hear clearly. Yeah.
You can or you can't?
We can hear and see your screen clearly, but someone can see. So.
Oh, okay.
Yeah, maybe there's a connection error in his side, I guess.
Alrighty, all right. So if most of you can see me, yes, that's fine. All right, no problem.
We can see you. Yeah, carry on. Yeah.
Right. Okay. Yeah. So I was saying that it'll be great if we had that infrastructure that we could give thumbs up to whoever we want to use our data, or say, hey, Mr. Facebook, Mr. Zuckerberg, sorry, I'm not happy for you to use my data. If you want to use that for any machine learning algorithm, for any prediction, for any recommendation system, you have to pay me, for example, right? In an imaginary world. I don't know when that infrastructure is going to happen, but that's a very good point that the paper brings up, the concern about the privacy of our data. Alrighty, I think I will only talk about this last part and then I'll wrap up. A very interesting point that the paper brings up is, when it talks about opportunities and challenges, we know that most of our machine learning systems works in one specific task. Cat versus dog problem, playing Go, protein folding problem, right? Recommendation system in Facebook, recommendation system in Netflix. So one task, right? And the thing is that we train the network once and leave it to work. We might come back a year later, retrain the model, change hyperparameters and all that, retrain, right? But this is not how we human beings learn, right? The way that we learn is that we are learning all the time. It's a continuous learning. So a big question for a researcher is that how can we construct some networks that can not only learn once, but it also learn continuously. Learn. So say, for example, for the whole time of a computer, the algorithm can learn, right? We know that we have active learning, for example, right? That when a new data comes to your database, the model will retrain itself with the model. These are technologies that these are all in this direction to get the models to be trained continuously, like the same as we human being, our brain and our learning system works. All right, so that's a great opportunity, and I think I'm going to wrap up there. Okay, I think I'm done. I just want to share here my LinkedIn profile. I'm happy to connect with all of you and learn from you and share knowledge with you. It'll be my honor to connect with all of you here. Okay, I'm done.
Okay, thank you so much, Hosein. It's like for me, it's like kind of listening the history of machine learning from the very beginning to the now. It's like you telling about the story for us. Yeah, thank you so much for the today's topic. So I will share your LinkedIn account in the chat, and then everybody can follow you and connect with you after the session. So we have like several questions in the chat. I think we can continue our like a Q&A session. So for the first question is like thank you for the presentation. As a radiologist, when I look at the backward generation feature, I imagine a future where the X-ray image will have automated annotation, radiographic interpretation, and we can spend more time teaching medical students doing this in the same time. So is there any comment or discussion on this comment?
Yeah, very good question. Very good question. Thanks for bringing up that. It's actually the machine learning applications in medical. I mean, the medical application of machine learning these days are one of the most important things, and it's actually really hard because you cannot make mistakes there, right? Because lives are at stake, right? It's actually a very important application for machine learning, and yes, in fact, we have big applications for detecting like features in X-ray images, in MRI images, for detecting images, and You can use a lot of object detection algorithms for that. You can use segmentation algorithms for that. And yes, but we can talk about it for full day. But yeah, there are a lot of things.
Yeah, I also hear about like a SEN or the like a bootcamp. So if I am not sure if he interested or not, like last time when I am talking with my colleagues and they mentioned about that, I am sending like a link in the chat. So it's kind of AI for healthcare bootcamp hosted by the Stanford Machine Learning Group, and they also did this kind of like a machine like medical related machine learning research, and also they also generate the X-ray data set for those kind of data. But I am not from that field, so I don't know detail about those information. But it's also very, very useful for the some like admin who is asking this question. Yeah.
Yeah. Well, actually, you know, there is this discussion going around that will radiologists be out of job in near future with AI coming into the play? Right. This is a big concern for you know, many jobs, and we can't really do anything about that. That's very less likely. I think radiologists will have the chance to, like you said, train students to how to use these algorithms, these models. And you know, all these models have to be labeled by human, the data sets, right? That's where we all verify the decision that is made by these models has to be verified by doctors, at least for a long time. So you shouldn't be worried about that. Also, this also brings to, let me touch on explainable AI. I'm pretty sure you have heard about explainable AI. It has a very strong application, in particular in medicine and in you know, medical prediction. And explainable AI is nothing but you know, when AI algorithm comes with a decision, it never tells us why. It never tells you why it came up with that decision. Say, for example, I told you this is a cat, right? But why? Did I look mostly at the ears, or I looked at the tail, or whatever? Explainable AI is important for that. For example, if you predict that this patient might have cancer, it must tell you why. Right? It must tell you that, okay, I looked at X-ray images and that had the most weight that I came up with the cancer decision. But there might also be other parameters that argue against that, against cancer. That's where explainable AI comes to play.
Yeah, thank you for bringing this one too. He also get a comment as like, AI will complement our work and make our life not easier. So, yeah. Okay, so let me move to the, like we are almost like a 3 minute less. So I would like to move to the next question. So that paper that we use is from the 2050 and we are on the 2022. Yeah, right. So, the question is, you also is a machine learning engineer in industry, and is there any advice or recommend route for the student to follow the trend in machine learning?
Yeah, that's a very good question. I need to be quick on that, but it really depends on where where's your interest. Are you interested in image and computer vision, or are you interested in like, say, tabular data and stuff like that? It's really hard for me to find the most you know, amazing part of machine learning. All of it is amazing. If you're thinking of getting a very good job, right? Only for, I mean, in a job perspective, recommendation system is the way to go. Like I said, it's making the most of money, right? The recommendation system first. But yeah, if and another very important one that I add to it is the new generative models, GAN models, generative adversarial models. right? As well as, language models, large language models. We have GPT-3, for example, and the most, the newest one, which is ChatGPT. I'm pretty sure all of you have touched it. If you haven't, please go in OpenAI website and have a play. It's amazing. You can interact with the language model. You can ask questions. It comes back with great answers. You can ask it to write a poem for you. You can ask it, and on the other side of like these generative models, we have like DALL-E that makes images for you, and then we have like Facebook's new algorithm that makes videos out of prompt. You give it a prompt, and it makes a video for you. There are a lot of evolution in these generative and fusion models. So I would say, if you want to follow something, fusion models and generative models, recommendation systems are great.
Yeah, thank you for pointing out the route. Start with the recommendation system and follow by your interest, and soon you can pick a hard direction based on your answer. Yeah. Okay. Is there any question or anything would you like to discuss with the Hosein here? So we still have we can open 2 or 3 minutes to have a discussion. Is there anyone would like to bring in the question and the topic that you would like to discuss? Where?
Don't be shy, guys.
So, yeah.
Okay.
Okay. Yeah. Is there no one? Let me wrap up the session. And thank you so much, Hosein, for like kind of interactive session today. Okay. Let me share my screen. Okay, can you see my screen? Yeah. So we have finished. Thank you so much, Hosein, for today's discussion and for the next week. So next week is our final week of Women in AI Machine Learning paper reading class. We arrived to week 10, and we would like to wrap up for this year paper reading class. So for the next week topic, we also bring the same topic again, and the web app like a closing session for the machine learning paper reading class. So we will use the same paper again with another speaker, and she will bring another kind of perspective from the machine learning field. So we will post all our information on the LinkedIn, and so do not forget to follow us. And also we normally update our information on the LinkedIn, Facebook, and if you have any query or related info, would like to know more about us, you can send an email to whyepad@womeninai.co. And also we record this session, and we will upload all of our machine learning paper reading club on the YouTube channel, Women in AI EPAD YouTube channel, and you can review all our session there too. So we also looking for the volunteer across the APEC chapter. If you would like to volunteer, volunteer with us, feel free to send an email to whyepad@womeninai.co. So thank you all for today's session. And if you have any feedback or something where you like to talk us, you can scan the QR code in here, and you can send a feedback and survey. You can send us the feedback from this URL. So thank you so much, everyone. And thank you so much, Hosein, for today's session. And have a good night.
Yeah, thank you. Have a good one, everybody.
Yeah, have a good evening, and bye-bye.
Bye.